From the ILC evasion video, we've known the process evasion is very critical in the passive ILC elements for any new design. Porting the old design or PDK update is that the process evasion for the transistor MOSFET active device still critical? Could you tell me why not? So we will show a few process evasions of the MOSFET for your references, and you should tell how important they are. To be clear, we are talking about the process evasion for MOSFET from the foundry SPICE models. Therefore, the first critical and fundamental evasion must have been the DCIV curve, which was the first topic we studied in the Microelectronics 101. As you can see, we can either choose the DC bias point from the DCIV curve or pick the proper MOSFET size W/L fitting the target DCIV curve and DC bias in your new design. Then, when you need to port the new design to another process but keep the same size layout floor plan. Therefore, a comparison of the DCIV between the original design process and the new process to be ported would help you decide how to adjust the MOSFET size properly in the new process. Lastly, in the process maintenance phase, the update PDK may push you to re-verify every block in the series, and that adds too much work. If you can do a simple DCIV comparison between the old PDK and new PDK, you may have an idea if you need to worry about the performance change and rerun a few other AC, trend, PSR, stability, etc. verifications over PVT. What's next? Correct. Second, after the DCIV over the PVT, you need to check the variability of the DCIV. As you should know, the most fundamental and robust analog biasing in the chip is to distribute the current and do the current meter locally. Unfortunately, the current ratio will vary because of a random variability. To make sure we can accept the current precision degradation, we must evaluate the device variability by looking at the threshold voltage matching parameter AVT. When you start a new design, you might want to apply an ideal current source dumping to a diode-connected MOSFET and run a simple DC simulation along with the Monte Carlo seeds. When you can also get the RMS variability of the threshold voltage or convert to the bias current variability in RMS. Either the threshold voltage or the current variability would help you choose the optimal device size W/L. Then, when you port the old design to the next process node, you can also compare the AVT between both process nodes to figure out what the expected variability could be, such that you can optimize the precision further or decide if the next process node is the proper process for you to meet the same or better precision. Again, when you receive the PDK update, the updated AVT can also show you if your next step out will degrade or improve the precision, which helps you decide what you to do the quick simulation without running lots of complicated Monte Carlo test benches. After we talk about two important verifications in the mission mode, what's next? Think about the power down mode image for 5 seconds. Bingo! What do you expect when you power down your circuits? Ideally, yes, zero current. But unfortunately, in a real circuit block, you may not be able to power down well, and you may have extra current you don't want, which is called linkage, instead of running the whole SOC to find out the total linkage current. Do you have a better way to getting a ballpark linkage number? Yes. What you can do is to characterize the linkage of a single gate, like an inverter. Then you can calculate how many gates you have in your SoC chip. Even though you don't run the power down simulation to get the linkage number in the whole SoC, you should get a pretty close number by multiplying the number of gates and inverter linkage. Then you should expect what the total linkage would be if you decide to move to another new process. For example, the linkage ratio between the 40 genetic 40G and 40 nanometer low power 40LP process node of an inverter is roughly 5 times. Then you should expect total linkage of a new process node 40G would be 5x if it keeps the same design. You can then decide if that's the right process node for you to think about if the existing your linkage budget. Lastly, you will get the update linkage number of an inverter quickly through the new PDK. Then you should be able to update your SoC linkage specification quickly. In addition to the digital gates power down mode, think about the digital gate mission mode in the timing images for 5 seconds. Great. We discussed the DTA, but before the DTA, you should evaluate the gate delay and the setup hold time of a flip-flop. Then, in your new design, you could apply the rule of thumb to judge if the process or the digital building block is good enough in your high-speed series. For example, you may know the setup time and clock-to-Q delay of the flip-flops and the fan-out 4 inverter delay respectively. Then you can add the total delay requirement to be setup time plus clock-to-Q delay plus 2 times fan-out 4 inverter delay to be the clock period needs to be. Then, given another gate delay and setup hold time of flops in the new process, you may decide if the same design would be faster or slower in the new process node, so that you can decide if that's the right process to you without too many design changes. Lastly, you can evaluate the gate delay and setup hold time of flops in the update PDK and see if that's the design change needed in the next tape out. In addition to the digital timing, what else can you benefit from the gate correlations? Great. If you recall the power integrity analysis, you may know the power supply introduced jitter not only depends on how much the supply ripple was, but also the gate delay sensitivity. In other words, the lower delay sensitivity, the lower introduced jitter from the supply ripple can increase the equivalent ion width. Another, from the low cost point of view, you can get the how to relax the supply ripple requirement and the package type if you choose a low delay sensitivity gate in your design, which is usually the ultra low VT devices in the minimal channel length delay you can get. Also, you can evaluate some niche applications that ultra low latency, as we discussed in the wide angle PAM4 series. For example, based on the gate information, you should know if the system latency meets your requirement. If not, you might want either reduce the number of gates to reduce the latency or apply to a better process before going too far. So, the single gate delay information can provide you a high-level understanding of either the power integrity or latency in an early stage. Okay, what else you might want to characterize? Correct. The noise will impact how big array you can achieve. Therefore, you might want to know your device's noise as early as possible before you put too much effort and realize that wasn't feasible. Then you can calculate how a simple device's thermal noise, flicker noise, or even the shot noise was at the beginning of the project to figure out if your target SNR is achievable in the device sizing or a chosen process. If not, you may want to move to another process or try different design techniques like noise cancellation or resizing. In addition to those performance requirements, what kinds of a scenario may you need the device information as early as possible? Bingo! Switching to a brand new introduced device such as FinFET or Gate-All-Around structures, process evasion plays a crucial role in developing and refining the manufacturing process to enable these advanced devices architectures. By either looking at the design rule menu of the new devices or running a few calculations through the foundry models, you will identify what kind of top-level topology you need to change to meet your design target. Here are the summarized images showing you why process evaluation for transistors, MOSFET, active device is a must, especially in your first day of design phase, or even the first of your project planning phases in choosing which process you like to go in your new project. For example, first, the DCIV curve or the noise data can help you estimate the area or your circuit topology is reasonable to implement in the amplifier, biasing, oscillator, etc. analog blocks to achieve the good SNR and low jitter for low bit array target in the first day or the first week kickoff meeting. Second, the device variability from the Monte Carlo would also help you understand how the proper sizing impacts on your area estimation in the early phase of your project. Third, the IDDQ evaluation would help you choose the right process to meet your power-down linkage target, in addition to evaluating the dynamic power at the early stage. Fourth, the gate delay not only help you confirm the chosen process can meet your maximum data rate speed, but also help you evaluate the power integrity quickly. Of course, those evaluation data should also help you optimize your design during the troubleshooting or improvement phases to make your design more reliable over PVT. Then, during the PDK update, you will also have the best idea of what should be verified without spending too much time on it. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting.